Um, my name is Ali Mirza and I am from Center for Future Materials at the University of Southern Queensland. Today I'm going to talk about the status of research on fiberglass rock bolting. First, I start to give a general introduction about polymer dowels or fiberglass dowels. Then I go through strength properties of fiberglass dowels, tensile strength, single shear testing, double shear testing in steel and in concrete, and then point shear testing. Subsequently, conclusions will be given, and at the end applications will be provided. Why fiberglass rock bolting? In recent years, it has been an increase in the number of projects that use fiberglass rock bolting, geotechnical projects that use fiberglass rock bolting for strata reinforcement. The reason is improvement in the strength property of fiberglass bolt, easy and safe handle ability of non-steel bolt, particularly fiberglass bolt. The fact that fiberglass bolts are weight, I think the weight is about 1 kilogram per meter, or even less than 1 kilogram per meter. And the fact that fiberglass bolts are relatively cheap when compared to a steel rock bolt, and is longer lasting and can be supplied at greater length, and the fact that fiberglass is resistible against corrosion, which is a very important for the design of rock structure where the harsh environment may corrode the steel rock bolt. Here we can see West Connect project, national level West Connect project in New South Wales, Sydney, where fiberglass rock bolt, as you can see it here, has been applied to stabilize the rock structure, the rock slope. Fiberglass dowels are made of glass strand mechanically pulled through saturated thermoset resin and heated. As you can see here, this process is called pultrusion. So as you can see, fiber goes through this guided plate and then resin heated and cured, and then it will be cut off at the end. Here you can see the fiberglass that goes through, as you can see it here, goes through the resin bath after the guide plate going through the resin bath, and you can see it as well here. These are the fiberglass rock bolt. We have fiberglass rock bolt in different strength, ranging from 10 to 30 ton tensile strength. Usually the diameter is the same, but with having different number of fiber, the tensile strength will vary, and with increase in the number of fiber, the tensile strength of the fiberglass rock bolt also will increase. Fiberglass dowel specification, typical specification is as following. As I said, the diameter is almost around 22 millimeter. Resin type is epoxy. Ultimate tensile strength is 790 megapascal. Shear strength is claimed to be around 180 megapascal. That we will investigate it in detail in this study. Cross-sectional area is 270 square millimeter. Elastic modulus 42 gigapascal, and weight, as I say, is less than 1 kilogram per meter, and density is 2 gram per cubic centimeter. So let's start with tensile strength. So based on accredited standard, the sample is cut firstly in 500 millimeter. 150 millimeter from either side are encapsulated inside a special cylinder, and then the whole assembly is positioned inside this inside the tensile testing machine and is subjected to tensile loading at the predetermined rate. The value of tensile load against displacement is recorded as shown in this figure. So you can see that the tensile strength increases, and then after that you're going to have a failure around 30 ton So the average value is 30 ton. And this is the sample after failure. So you're going to have tensile failure in the sample. You can see here that there is another set of data which is a bit away from the rest of the data, because most of the data are close to each other. The reason is another test was carried out with the exposed length higher than 200 millimeter. So the intention was to see how the exposed length of the sample going to affect the result of tensile strength. It was observed that the peak value is almost the same, around 30 ton. However, the stiffness decreases with increase in the exposed length of the sample. We did not just test samples produced in Australia. Sample produced overseas also tested in this investigation. We call here black fiberglass dowels. Black sample, so it's like color coding, so black and color. So black one is the foreign product, and the colored one are Australian made. So a tensile test was conducted on black fiberglass as shown in this figure. So vertical axis shows load in kilonewton and horizontal axis extension in millimeter. So you can see the tensile strength is around 27 ton as shown here, and this shows the photo of the sample after failure. Single shear test or guillotine shear testing was carried out to determine pure shear strength of the sample. So sample were cut in small pieces and were positioned inside this guillotine box, and the whole assembly was again positioned inside the tensile testing machine. So you can see here that by having extension, the sample is subjected to shear loading. This figure here shows the value of shear load in vertical axis in kilonewton versus shear displacement in millimeter. So the peak value is around 5 ton for colored fiberglass. The same test was repeated for black fiberglass as shown in the right picture here, where the left picture shows the color fiberglass single shear strength. It is concluded that the black fiberglass has shear strength around 1 ton higher than color fiberglass. The result of the test are tabulated in these two tables for color fiberglass in the left side and black fiberglass on the right side. So the average shear strength for color fiberglass is around 51 ton, and for black fiberglass is 57 ton. So black dowels are 13% stronger than those of colored fiberglass dowels. So shear strength testing was also carried out in steel double shear testing, as you can see here. So the difference between guillotine box and steel double shear testing is that you have two cross-sectional area of shearing rather than one that you have in single shear testing. So the sample is cut in a small length and then positioned inside this hole here. So it goes inside of the instrument, and then the whole assembly is subjected to compression, and we're going to have shear in these two cross-sectional area. So the result of the test is shown in these two tables. The left one shows the data for colored fiberglass dowels, and the right one shows the data for black fiberglass dowels. As shown here, black fiberglass dowels is almost stronger in the order of 1 ton when compared to that of colored fiberglass dowel, or 20% stronger. Black fiberglass dowels 20% stronger than colored fiberglass dowels, almost. In order to simulate field condition where you have a strata and you have pretension and grout around the sample, double shear test was developed. This picture here shows the shear box, double shearing box, And here you have the concrete sample for double shear testing. So double shear testing consists of three concrete blocks, two outer and then one in the middle one, which is the bigger one. There is a hole in the sample where the fiberglass goes inside and is encapsulated using the hole on top of the sample. In order to produce the rifling, the rod that is positioned inside when concrete is cast, the rod is wrapped with a wire to provide the imprint of the rifling. So once the sample is made, the rifling as experienced as we have it in the field can be seen in the sample. So double shear test is carried out to simulate shearing conditions as experienced in situ, and the intention is to observe the effect of concrete or strata strength, the uses of the strength on a strength property of fiberglass rockboard, to investigate the effect of axial load or pretension value on shear strength of fiberglass rockboard, and then how the type of the grout and resin can affect the shear strength of fiberglass rockboard. This picture here shows the mold that was recently made in Centre for Future Material at the University of Southern Queensland for casting concrete block. These are used to make the hole on top of the sample, and this is the rod, and then you can see the wire around that to make the imprint of the rifling. Once the sample is cast, the fiberglass is positioned inside the concrete block, and then the whole assembly is positioned inside the compression testing machine, and the middle block is subjected to compression at the predetermined rate, which is around 2 mm per minute. The value of shear load against shear displacement is measured. After testing, the sample is dismantled and the quality of encapsulation is investigated. As you can see here, it was a perfect encapsulation, and we can observe that the imprint of rifling is captured in this test. So some of the tests are shown in the following slide. So this shows double shear test of fiberglass dowels in 40 megapascal concrete. So the vertical axis shows the load in kilonewton, and horizontal axis shows displacement, shear displacement in millimeter. Bearing in mind that because we are doing double shearing, the value that we achieve should be divided into two in order to come up the shear strength of the sample, or the whole system, rather than saying the sample, better to say the whole system. The top data here shows shear, and below here shows the axial load. So indeed, if I go back to this slide, a load cell was positioned behind this barrel and wedge, let's say it, or yes, barrel and wedge was positioned there to measure the variation of axial load against shearing, and actually one position, one load cell was positioned here and another one there behind this knot, rather than barrel and wedge, saying knot. A load cell was positioned here and another load cell was positioned here to measure the variation of the axial load during shearing, and the average value of that is shown here in the data below here. So it is observed that the shear strength using the shear strength of fiberglass dowels using double shear testing machine is between 20 to 20 say 7 tone, bearing in mind that it should be divided into two to come up with the pure shear, to come up with the shear strength of the system, because we have two shearing surfaces. What else we can observe here is that at the point in which we have failure In the same point, we have almost failure in axial load as well. So it's another way to check the precision of the data. So you have again here, so failure, the peak value in axial load as well, and then the same thing here. So you have the peak value both here and here. Double shear tests were also carried out in 60 megapascal concrete block, and the same type of the data you can see here. So vertical axis shows load in kilonewton and horizontal axis shows displacement in millimeter. Data below belong to the axial load variation, and on top shear load variation. We can see the shear strength varies from 20 to 27 ton depending on the value of pretension, bearing in mind that the value should be divided to 2 to come up with the shear strength of the system. So the sample was dismantled and the quality of encapsulation and rifling was observed, as you can see in this picture. A good encapsulation and rifling were captured in all the samples. So the value of shear strength, peak shear strength, and shear displacement corresponding to peak shear load for 40 megapascal and 60 megapascal concrete block are shown in these tables. The table on top is for 40 megapascal and below 60 megapascal concrete block. It is observed that the type of the sample and the initial pretension value will affect the shear strength, which will be further investigated at Center for Future Material for various type of pretension, for various dowels type, and the type of the concrete blocks. Point shear test was carried out to determine the axial and perpendicular shear strength of fiberglass dowels. Samples were cut parallel and perpendicular to the cross section of the sample. The small thin sample was positioned inside this point shear testing, and the whole assembly was positioned inside the compression machine, and shear strength was determined. As you can see here, samples cut perpendicular to the dowel axis shows shear strength around 22.35 megapascal, which is this one, and the sample cut parallel to the dowel axis, which is this one, shows shear strength of 104.01 megapascal. So almost the ratio of sample cut parallel to the dowel axis divided to sample cut perpendicular to dowel axis is around 4.65. Tests were repeated for black fiberglass dowel, and the ratio of 3.34 was achieved. So as a conclusion, guillotine method of testing dowels in shear yield lower shear strength values than testing dowels using double shear testing in concrete. Double shear testing in concrete present a realistic way of simulating the strength property of composite material in rock and in situ. Shear value of fiberglass dowels is a function of pretension value, concrete strength, and type of the grout, strength of the grout. And based on the point shear testing, it was concluded that dowels are weaker in shear tested perpendicular to dowel axis strength than parallel to strength. So where we can collaborate, application of this research study can be in application of fiberglass bolt in rock slope, fiberglass bolt in tunnels, and advanced numerical simulation. So as shown in the second slide, fiberglass bolt already has been used in many projects, in many civilian projects for rock slope stabilization. For instance, in Sydney national level West Connex project, where fiberglass dowels have been used to stabilize rock structure. In the same way, it can be used to stabilize tunnels, and also advanced numerical simulation using 2D or 3D finite different software such as Flag 2D and Flag 3D or UDEC or 3D that can be used to simulate the stability of rock structure, such as tunnel and slope. For instance, if in this project finite difference software has been used to design to come up with the best support system, the number of cable bolts and rock bolts for this tunnel, for this rock structure. In general, the benefit will be a reduction in the maintenance cost by implementing corrosive resistant and relatively cheap fiberglass bolt. Improvement in the design lifetime of support system and increase overall safety through advanced numerical simulation. So we have a fantastic research team consisting of Professor Najaziz and Dr. Jan Nemchik. Professor Najaziz is adjunct professor of University of Southern Queensland and a renowned, well-known professor in the field of geomechanics and the leader of Rockbolting and Strata Control Research Group at the University of Wollongong. We have also a dedicated PhD student that is working on fiberglass rock bolting, and with the view of coming funds, we expect to have more PhD students to work on either shear or axial load transfer mechanism of fiberglass rock bolt and advanced numerical simulation. Thank you very much, and please let me know if there is any question. Thank you.